Alright, so today we are talking about optimization. Optimization is this really big field in math, and it's like one of the things that is pretty cool. I think that it's one of the more like applied things, and optimization has a lot of implications in well, any kinds of things that you're trying to maximize or minimize, things like profits, losses, if you're trying to minimize, I don't know, exposure to things, or whatever else you're trying to make the most or the least of. Optimization is the way to go. So, yeah, let's get into it. So the problem-solving strategy for optimization problems is figure out what your variables are and draw a picture and label everything, and then determine what you're trying to maximize or minimize, and figure out what your range is, write a formula, and then write any independent variables in terms of the thing before, and then identify like something if there's like a constraint, and then figure out what your mins and maxes are. Wow, so complicated. You know what's easier? Step 1, write down the variables and draw a picture. Connect the variables that you have in step 2. Connect them having a constraint, something that's limiting what you can do, and an objective function, the thing that ties it all together. Then figure out what you're trying to optimize, which is the objective function. You're trying to maximize or minimize that. And how do you find extrema? Well, you need to differentiate. Set it equal to 0. Or find when it's undefined. Get those points and use them to figure out what your extrema are. Check your endpoints, because remember, we always have to consider what our endpoints are for our domain, because those might be our extremas. And then at the end, just make sure that your answer makes sense. So let's try it. So what are the points on the graph of y equals 4 minus x squared? So let's draw that. It's a parabola facing downwards. We're gonna boom, 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 and there. Okay, so we have this parabola. Okay, cool. So we got a parabola. Y equals 4 minus x squared. Where are the point or points that are closest to the point 0, 2? 0, 2. Boom, right there. So we're probably looking somewhere there and probably somewhere like that. So where are those points? Well, how are we looking at this? We have our picture, and now we need to figure out what our variables are. We are looking to minimize, closest means minimize, the distance. So we should use the distance formula. Distance equals some really bad square root of x2 minus x1 squared plus y2 minus y1. This is just a Pythagorean theorem that also arose in other countries that weren't Greek. Maybe not even attributed to Pythagoras, but whatever, we'll call it the Pythagorean theorem because reasons. And the point that we're looking at is the point 0, 2, so we can just substitute that in. You want to put it in for x1 and y1? Yeah, sounds good. So d equals root, and x we're going to say is our input. So we're going to keep x, this x we're going to keep it. X minus our x input, which is 0, squared, plus y, which is there, minus 2, because that is our point y1. And now, this is our objective function. But it's a function of both x and y right now, and we don't like that, because it's really hard to differentiate with respect to two different variables at once. So let's just use our constraint, y equals 4 minus x, because that is how we are constraining what the points that we're looking at are. We're putting them only on this parabola. So we have d equals root x minus 1 squared is just x squared plus y minus 2, where y is 4 minus x squared minus 2, and we're squaring that quantity, and we can simplify so that that is what? Root x squared plus 2 minus x squared quantity squared. That's our d. Okay, so that's our objective function. What do we need to do next? Differentiate. We need to differentiate with respect to x because that is what's changing. So we have d. Oh, d is a bad choice. D prime of x, the derivative of d, is, we got to chain rule this, so we got 1/2 x squared plus 2 minus x squared to the negative 1/2 power times, and I'm going to do really bad notation here, I'm going to multiply down here, by parentheses 2x plus 2 times, 2 minus x squared times negative 2x. It's a good chain rule. Wow. And then we can simplify a little bit, right? So what do we get? D prime of x equals, we have this 1/2, and then we have 2 as a factor here. So pew, pew, pew. We have x plus 2 minus x squared times negative 2x all over x squared plus 2 minus x squared to the 1/2 power in our denominator, because this is to the negative 1/2 power, so that's going down there. And then this is our numerator right there. Okay, and then we need to do some more algebra. Let's do it. Okay, so what do we need to do? We need to simplify our derivative. So d prime, change colors, of x equals x minus, what is this? 4x plus 2x cubed all over root x squared plus 2 minus x squared. Okay, so we're looking for when, I guess we can simplify further, d prime of x is negative 3x plus 2x cubed all over this, which is what, x squared plus 2 minus x squared, and this is always going to give us positive values, right, because we have something squared plus something else that's being squared, and we're adding those together, and so positive plus positive is always positive, and so when we're rooting that, that's totally fine. Even 0 still works because 2 minus 0 is 2, and then when we're squaring that, we're still getting a number in the denominator. So when we're looking for when our derivative equals 0 and when our derivative is undefined, our denominator is never going to be 0. So our function is never undefined. But our derivative is going to equal to 0 when 0 equals the numerator. Do you remember did you ever see the 0 divided by a number is okay, but a number divided by 0 is no. That's fun. I like this. It's funny. So negative 3x plus 2x cubed, our derivative, equal to 0. When does that happen? 0. Let's factor out an x, so we have negative 3 plus 2x squared. And when does that happen? When x equals 0, and when 2x squared equals 3, which is when x is plus or minus root 3/2. Alright, so we have our critical values. Now that we found our critical values, we need to figure out what they are. So let's use a number line to organize our thoughts. And let's put our critical values on our number line. So we have negative root 3/2 and positive root 3/2, and we need to plug in some numbers. So well, into our derivative, right? Because the first derivative test tells us that if our function has a derivative that goes from negative to positive, that means that we have a minimum, because our function's decreasing and then increasing, so we get a minimum there. And are we looking for a minimum? Let's check back to our function. What do we need? We are looking for closest to the point 0, 2, so closest means minimum. So we're trying to minimize. We're trying to find when our derivative goes from negative to positive. So plug in like negative, I don't know, 1 billion, and what do we get? Here we have negative 1 billion minus 1 billion, which is still negative, minus 2 times negative 1 billion cubed, which is still negative, so we have negative over something that's always positive. So negative on that side. What's something that is between negative root 3/2 and 0? Well, we can just plug in like something pretty close to 0, like 0.1 or something. So 0.1 minus 4 times 0.1, which is negative, plus negative 2 times, or negative 0.1 plus 4 times 0.1, so it's positive 0.3, plus 2 times x to the third, so that's negative 0.0002. So it's still going to be positive over something that is always non-negative. So we got positive right there. And we're just going to alternate signs, because in our denominator, we're not changing signs at all. But once we cross over 0, because x equals 0 is something that we're crossing over, then our numerator is going to change signs. So we're going to get negative here, and we get positive there. So where are we changing from a negative derivative to a positive derivative? At plus or minus root 3/2. So the goal is to find the points on the graph that are closest to the point 0, 2. So we need to plug in to find points. So root 3/2 plus or minus is root 3/2 squared, and 4 minus gives us our y value. So y equals what? 4 minus 3/2. So y equals 4 minus 3/2, that's what, 8/2 minus 3/2, 5/2. So 5/2, and so we have the points negative root 3/2, comma 5/2, and the point over here, I'll put that in a different color, positive root 3/2, comma 5/2, as the points on the graph of y equals 4 minus x squared that are closest to the point 0, comma 2. Whew! We did it. Alright, so what about this one? We have 600 feet of fencing that is to be used to enclose 2 fields. So 2 fields. And the perimeter of these 2 fields has got to be 600 somehow. One is to be a rectangle twice as long as it is wide, and the other is to be a square. So let's draw a rectangle, and let's draw a square. Square field must contain at least 100 square feet, and the rectangular one must contain at least 800 square feet. What is the greatest area that can be contained in the 2 fields? So the rectangular field needs to be twice as long as it is wide, so x and 2x are the dimensions. And the square field needs to be not necessarily the same variables, so let's just change the variables. So the dimensions on the square field are going to be y by y. So our constraint is that the square field must contain at least 100 square feet. So that's this must be 100 square feet at least. 100 needs to be less than or equal to y squared, the area. And the rectangular one must contain at least 800 square feet. So 800 is less than or equal to x times 2x for this area. We get, what, 2x squared. So what's the greatest area that can be contained in our two fields? Well, we can, so the area contained in the two fields is what we're trying to optimize. Our objective function is the area, which is contained in the two fields, which is 2x squared plus y squared, the areas of the two fields. This is kind of messy though, because we have a couple of variables going on in our objective function, so we're kind of nervous and we need to figure out how to consolidate our expressions into something that we can handle. How do you think we can do that? Well, we are limited by 600 feet of fencing, so that's another constraint. We have 600 must be equal to all of these fences, and this is x and this is 2x. So we have 4y plus 1, 2, 3, 4, 5, 6x. And this equation must hold true. So now we can rewrite our objective function, a equals 2x squared plus y squared. This is our objective function, with our constraint where 600 equals 4y plus 6x. For no particular reason, I just don't feel like writing a bunch of y's today, so let's solve for x. And what do we get? So let's solve for y so that we can substitute that in for our y expression and have our entire a equation, our objective function, only in terms of x. So let's try it. 600 minus 6x equals 4y, so y equals 300 minus 3x all over 2. I think so. So then we can have our area in terms of only x's, because we have 2x squared plus how much? Y, which is 300 minus 3x all over 2. So 300 minus 3x all over 2, and that quantity is being squared. And now we have our objective function only in terms of x's, and so that's good. It's not a bad thing. Should we get a little bit of domain on here? So we know that 100 is square rooted is 10, so y needs to be greater than 10, and 800 divided by 2 is 400, and then square root of 400 is 20, so x needs to be at least 20. So these are domain things, so that's nice. And what should we do now? Well, we drew our picture, we established our variables, and we got our objective function in terms of only one variable using our constraint. So now we need to differentiate. And a is a function of x, which was the goal. So a prime of x equals, and we got to take our derivatives, so 4x plus, and I guess we should chain rule, so 2 times 300 minus 3x all over 2 times the derivative of our inside, which is negative 3 halves, because the derivative of 300 over 2 is just 0, because that's a number. And then the derivative of negative 3x over 2 is just the slope, which is negative 3 halves. We can cancel out some of these 2's, and we can write this a little bit nicer. So we got what? A prime of x equals 4x. 300 times negative 3 halves is negative 900 over 2. 450, okay, and then negative 3 halves times negative 3x is plus 9 halves x, okay? So this is 8 halves x and 9 halves x, so we have 17x over 2 minus 400 is a prime. That's a line, so it's never undefined. But when is our, so we don't have critical values when the derivative is undefined, but we can find where our derivative equals 0. 17x over 2 minus 400. And what do we get? 400 equals 17 over 2, so 2 over 17 that we're multiplying is x, and that's kind of, oh wait, that's not 400, that's 450. Oof. 450 is 900 over 2. I had to take a break between filming because I was getting sleepy and losing like algebra. Okay, so x, so this is simplifies 2 times 450 is 900 again, and 900 over 17 equals x, and that's a critical value. Okay, and we actually don't have any other critical values except for our domain thing that we found up here, that x needs to be greater than 20. So what should we do from here? Well, we should probably organize our thoughts. I think we can also take this 10 must be, that y needs to be greater than or equal to 10, and relate that back with our y expression. So let's try that as well, so that we can have just another endpoint to fully check all of our endpoints. So we have 10 is less than y, which is 300 minus 3x over 2. And then we got, what, 20 is less than or equal to 300 minus 3x. What is that? 280. Negative 280 is less than or equal to negative 3x. And then we would divide by a negative. We need to change our the direction of our inequality, because like 5 is less than 7, but negative 5 is greater than negative 7. So we get 280 over 3, and that's not nice because 280 doesn't have 3 as any of its factors, is greater than or equal to x. So now we have two endpoints. We have 280 over 3 is our upper endpoint, 280 over 3. And our lower endpoint for where our x can be is 20. And then we have a critical value. Where did it go? We have the critical value of 900 over 17 as a potential max or a min. So we need to think about what our derivative is. So a prime, what is a prime when x is between 20 and 900 over 17? Well, we can think about this line as a helper for that, because the line has a positive slope, right? This line has a positive slope and it has an x-intercept, or y-intercept of negative 450, so our derivative is going to be negative. A prime of x is less than 0 on this interval, and because down here, right, a prime is valued at negative, and then a prime is going to be positive. A prime of x is going to be positive on this interval up here, because our value of our derivative is positive, and then we have endpoints that we can't go past. So if we're going from a prime is like negative to a prime is positive, that means that we found a minimum. Was that the goal? I don't think so. I think the goal was actually to find a maximum, right? We were trying to, the greatest area that can be contained in the two fields. So I guess we need to check our endpoints. So our endpoints are 20 and 280 over 3. And those are what we need to plug into our A of x. So let's do it. So A of x is 2x squared plus, I'm just copying from right here, but so that we have more space. 300 minus 3x all over 2 squared, and then we're checking x equals 20 and x equals 280 over 3 because we had a garbage minimum as our critical value. Not garbage, just not helpful for the context of the problem that we're looking at. So let's plug those in. Why don't you plug those in, and then I'll put a question here. So A of 20, when you plug that in, what do you get? Do you get that? I hope so. And if you plug in 280 over 3, what do you get? Do you get that? I hope so. And which one's bigger? This one's bigger. So, what's the actual answer to our question? What's the greatest area that can be contained? So we found an area, we don't need to give the dimensions. The greatest area that can be contained in our two fields, given that we only have 600 feet of fencing and we have to have one square and one rectangular, is 17,522 feet, 0.222 feet squared. Whew. Need more coffee. Alright, so we have a cone of altitude 7 centimeters and base radius 5 centimeters. It has a cylinder inscribed in it, with the base of the cylinder contained in the base of the cone. So the base of the cylinder is contained within the base of the cone. Probably should have changed colors. The base of the cone is the red plus the blue-green thingy. Okay, so that's the base of the cone, and the base of the cylinder is inside it. Find the radius of the cylinder of maximum lateral area. And lateral is where you're looking at only the sides. So you're not looking at the area of the top or the bottom of the cylinder. You're just looking for the wraparound like side of it where you're looking at this part. Just with like an open top and an open bottom. Like that. Okay, so it's really nice that we have a cone, because what was a nice thing that we used with cones in our related rates problems when we had like water coming in or out of a cylindrical tank or a conical tank, or we were having like gravel or sand being formed into a conical pile. We had similar triangles. So let's label those nice similar triangles that we had. So we have the altitude of the cone is 7 centimeters. The base radius of the cone is, oh, that's really big. The base radius of the cone, going from the center of the cone out to the edge, that is going to be 5 centimeters. So that is 5 centimeters. And we lost that. That was a centimeter. 7 centimeters, and we have a cylinder that's inscribed in it. And the cylinder that's inscribed in it has a radius and it has a height. We can say that this radius, let's call it x, and this height is, let's say, y. But we also know, or actually let's call the height up here y, so that we can use our similar triangles a little bit more nicely. So that means that the height of the cylinder is the total height of our cone, 7 centimeters, minus this part, the y, and that leaves us with this section right here. So we have, this is 7 minus y. Okay. So we have similar triangles that are happening here and there. Wow, so many colors. Okay, but the little blue triangle defined by x and y, and the bigger green triangle where we're using our given dimensions. So we have x over y, the base over the height of our triangle that's on top of the cylinder, is equal to 5 over 7 from our dimensions of our cone. So that's an expression, or that's an equation that advances our cause of relating our variables to each other. But I think that that's probably more of a constraint than an objective function, because we're looking for the radius of the cylinder of maximum lateral area. So maximum gives us a hint that that's what we're trying to optimize, and lateral area is probably the function that we're trying to look for. So what's the lateral area of a cylinder? I almost said cone. What's the lateral area of a cylinder? Well, that's just the circumference of our cylinder times the height of the cylinder, because when you unravel a cylindrical object, the lateral side of it, right, like a soup can or any sort of can wrapper or label, it's a rectangle. It's a piece of rectangular paper. And the height of the rectangle is something like h. We're probably going to get it is 7 minus y, though, just a hint. And this part is the circumference of the circle, which is 2 pi radius, which is x in this case. So the area is 2 pi x, which is the circumference of our cylinder, times the height, which is 7 minus y of our cylinder. And well, we want all of this in terms of the radius, because that's the goal. Find the radius. And the radius we're saying here is x, isn't it? We have x. X is the radius. X is buried within all the colors. Sorry about that. So we need to substitute using this constraint so that we have our area function only in terms of x. So we need to solve for y. So we got what? 7x equals 5y. So this means that y is 7x over 5. And so we can substitute that in here for our area. Area with respect to x is 2 pi x. 7 minus 7x over 5. It's a bad x, that looks like a star. X over 5. So we have our objective function. Lovely. we need to differentiate. Wow. We need to differentiate. Set it equal to 0, or find where it's undefined, although this seems like it's going to be a line once we take our derivative. So we're not going to have any parts that are undefined. But so we'll just look for our derivative. A prime of x. I guess we can product rule this, right? Because we have this function times, or that expression times that expression, or function times function. So 2 pi x times negative 7/5 plus 2 pi times 7 minus 7x over 5. We can combine some like terms. Let's see if I'm awake enough to do this. A prime of x equals negative 14 pi over 5x plus 14 pi minus 14 pi over 5x. So then we have 0 equals, we take our derivative, set it equal to 0. So we have 14 pi minus 28 pi over 5x. So that means we have 28 pi over 5. X equals 14 pi. The pi's cancel. 28 and 14 cancel to 2 and 1. So we have x equals 5 halves centimeters. Now we need to make sure that that's actually a maximum because, I don't know, 5 halves. But look at this line. What's it going to look like? It's going to be a line with a negative slope. So we're going to have a prime of x is positive on the left and a prime of x is negative on the right. If you don't believe me, then just plug in some numbers that are greater than or less than 5 halves into our derivative and then see what you get. So we have our a prime is positive and then our a prime is negative. So going from positive to negative gives us a maximum, and I think that's what we were looking for. Let's check the problem one more time. Find the radius of the cylinder of maximum lateral area. So that's actually, yeah, we did it. Cool, we did it. Good job. The maximum lateral area is given by x equals 5 halves centimeters radius for our cylinder that is lost in the fray of colorful things. Alright, last one. A glass fish tank is to be constructed to hold 72 cubic feet of water. So that's the goal. Its base and sides are to be rectangular. The top is, of course, to be open so your fish don't suffocate. It is to be constructed so that its width will be 5 feet, but the length and height are variable. So we have, this is a very poorly drawn fish tank. Wow, that was really bad. Okay, so we have the width needs to be 5 feet, but the length and the height are variable. Building the tank costs $10 per square foot for the base, so that would be 5L, right, is the base of this fish tank, and that's going to be $10. So the cost of that is 10. And $5 per square foot for the sides. So we have the sides, this right side, and the right and the left side are HL, so that's 5HL, and the front and the back are going to be 5H. So that's $5 times 5H, and that's going to be the cost. So that's going to be our cost equation. However, we need to figure out how to connect our length and height so that we're not looking at a function that has two different variables in it for our objective function. So where could that be? We have 72 cubic feet of water. That's part of our constraint. So that gives us, well, the volume is length times width times height, isn't it? So we have 72 is 5 times the length times the height. So let's solve for L, because my L's get kind of messy. So we have 72 over 5h. Sorry, that's really low down there. 75 over 5h as L. And so now we have our constraint and we have our objective function. So we'll put our constraint into our objective function. I'm going to change this order around. So the cost equals 50 times L, which is 72 over 5h, plus 5h times 72 over 5h. Oh, that's lovely. And 5 times 5 is 25 times h. And there's no L's there, so I just leave it alone. Okay. So, what do we get? We get C equals 50 over 5 is going to give us 10. So then 10 times 72 is 720 over h. And then, oh, something happened. What happened? Oh, I didn't double the right and the left side. So 2 times that and 2 times that. Wow. 2 times that and 2 times that. Okay. So then we have plus 144, because that canceled with that, but we have 2 times 72, plus 50h, right? Because we needed to double the cost of the right and the left sides, because otherwise you only have 3 planes of your fish tank, and then it's going to be not a good fish tank. Okay, so now we need to differentiate. So C prime of h is negative 720 over h squared. That's the power rule. Plus derivative of 144 is 0 plus 50. And then we can solve. So we get h, whoops. We get that our derivative, C prime of h, is undefined at h equals 0. But if you have a height of 0, then you still don't have a fish tank. So we're not that worried about that. So C prime of h equals 0. And then we solve for h, the height. And we get 720 over h squared equals 50. Those zeros cancel. And we get h squared is 720 or 72 over 5. So then h is going to be something like 3.795, and we need to make sure that that's going to be what's the goal? Least expensive. The goal is least expensive. Therefore, we need this to be a minimum. 3.795, and then if we plug in like something like, I don't know, 1, plug in 1 into our C prime. C prime of 1 is going to be negative 720 plus 50, which is negative. And then C prime of like 50 is going to be 720 over 50 squared is like 2500. So significantly smaller than the magnitude of 50. So C prime of like 50 is going to be positive. If we go from negative to positive, that means we have a minimum. So we found the height of our least expensive tank, but now we need to actually find the cost. So answer the question. The cost of the least expensive tank means that we plug into our cost equation, which was here, but I'll copy it down there. What is it? Cost with respect to height is 10 times 5L, which is, no. Oh, here it is. Okay. Cost is, oh my gosh. Cost is 720 over h plus 144 plus 50h. Plug in this h, and what do we get? I think maybe something like $523.47, which is a very expensive fish tank, but no matter. It's fine. Maybe your fish are worth it.